Today in mini lecture 22, we're going to cover step function. We're going to basically define the step function. We're going to talk a little bit about step response, and we're going to talk about zero state circuit. Those three things are somewhat important. You will find them both in your homework. You'll find them also if you look in any kind of technical journals, those things might creep in. So we are going to talk about that. So let me go to the document camera and start showing you. I'm going to basically do an example after I define the step function here. So let's go to the document camera here. Okay. So again, today we're going to talk about step function. Step response of first order circuits. And we're going to talk about zero state circuits. Okay, that's what's on our plate today. And we'll do so also via some examples to show you how things are. The first thing I'm going to do essentially is flat out start by defining the step function. And you're going to see how the step function looks familiar in a second. The step function is a function essentially that is zero, again, that has a value zero, and at t equals 0, it goes up to 1 and it stays. Okay, so that's the step function here. Okay, that's the step function. All right, so the step function at before 0, it's 0, and then at 0, it kicks in. You can essentially extrapolate that the step function basically acts like a switch, switching from 0 to 1. So we call this function u of t. Okay, so it's a function that's 0 for t less than 0 and 1 for t greater than 0. Between essentially at time 0, it's undefined. Okay, it's undefined. So this function happens to be important because in essence, what this function is saying, you're flipping a source on. You essentially, the source is off and you go and flip it on via a switch. So you're flipping a DC source, in this case, from 0 to 1. Okay. So I'm not going to use this very much in examples, but you will find that in some of the homework examples that we have, and also in many textbooks, we'll use the step function as a way to essentially exemplify a switch. So, in a sense, so let's go ahead and essentially look at an example here just to illustrate what a step function can do. So here I'm going to look at a particular circuit. Let's say 2 ohms here, and then I'm going to put a 2u of t. So I'm going to put a voltage 2u of t. There is a resistor here, okay? And there is a capacitor. Let's say a capacitor 0.2 farad here, okay? All right. And then obviously the typical question, and we could ask any types of question. Let's assume that that we're doing this voltage across the capacitor. Calculate VA of t for all times. Okay, so first of all, when you see a circuit like that has a source that has a step, the step function, any response essentially can be classified as a step response to the step function. Okay, the step function obviously is multiplied by 10, but that's what, when we're talking about step response, is when one source, the source in the circuit is a step function. Okay. So you look at this just like we would see a switch at time t equals 0. So we solve the circuit for 2 time period. Okay. For t less than 0, what do we have? That voltage source is 0 by virtue of defining the step function. So for t less than 0, we have this. We have a voltage source which is 0, the 2 ohms. And I think this is 4, by the way, the 4 ohms. And the capacitor with a voltage VA here, the 0.2 farad capacitor. Okay. Obviously, for t less than 0, this circuit's been like that forever, as this function shows. So there is no source in the circuit. So the circuit essentially is totally has no power. So everything is 0 in the circuit here. So VA for t less than 0 is 0. Okay. So this is what we call a zero state circuit. So a zero state circuit is a circuit with the initial energy stored, initial energy, so initial condition, in the inductor or the capacitor in the L or C is 0. So this is how we define a zero state circuit. A zero state circuit is a circuit with the initial energy either in the inductor and the capacitor is 0, and the initial energy is the initial condition. So the initial condition for that circuit is 0, just like the case that I'm showing you here. Okay, so this is a zero state circuit. All right. So, and of course here, the next thing we do, we solve for t greater than 0. And what do we have when we do that? This part, the voltage source becomes 10 volt, because obviously U of t goes to 1. And then we have 2 ohms here, the 4 ohm resistor here, and the capacitor, essentially 0.2 farad. Okay. So that's the circuit for t greater than 0. And the initial condition on VA, I'm going to be using here, I'm going to be using nodal analysis. So here is my, I'm going to put my reference node. This is V1, and thus this is VA. Okay. And then furthermore, I'm going to put currents on my passive elements. I1, I2, I3. Okay. So that's setting up in a typical nodal approach here, and source equation here. I'm going to say V1 is 10 volt. That's pretty simple here. The reference node is here. I have also a super node, but I won't do much about it because it has the reference node. Okay, so that's my super node, but the source equation for the voltage source is 10 volt. And then we have KCL at VA. So what do we have here? We have I1 equal I3 plus I2. Okay, that's the KCL at node VA right there. Current coming in equal current coming out. And then we do Ohm's law. So what are the Ohm's law equation here? I1 is equal to V1 minus VA over 2, and I2 is VA over 4. Okay, those are the 2 Ohm's law equations for our resistors right here. And at which point here, I bring the Ohm's law into the KCL equation. So KCL plus Ohm's law. What do we have? I1, V1 minus VA over 2 equal I3 plus VA over 4. I can multiply the whole thing by 4. So what do we have? We have 2V1. We have 2V1 minus 2VA equal 4I3 plus VA. Okay, put everything on one side. So what do we have? We have 2V1 minus 3VA minus 4I3 equals 0. Okay, so that's the KCL plus Ohm's law equations, just putting the Ohm's law into the KCL. All right. Of course, V1 is 10 volts. So what do we have here? V1 is 10 volts. So we have 20 minus 3VA minus 4I3 equals 0. And then we're going to, for the capacitor, we're going to say I3 is equal to 0.2 dVA dt. Okay, and we're going to essentially use that in the KCL equation. So what do we have? We have 20 minus 3VA minus 4 times I3, so minus 0.8 dVA dt equals 0. And you can see the differential equation coming here into play for that. Essentially, I can send the 20 on the other side. So we get what? We get minus 0.8 dVA dt minus 3 VA equal 20. Equal minus 20. How's that? Okay. So the normalized differential equation is what? Just normalized by divided everything by minus 0.8. We get dVA dt. All right. Plus $375 VA equal 25. So this is the differential equation that we have essentially for t greater than 0, solving this really two-node problem here, one being essentially a source equation here. So you see the differential equation now when we have step function in the circuit, we have a right-hand side which is not 0. So the right-hand side essentially is a constant, but it's not 0. So we know now that VA for t greater than 0 is equal to C1 e to the minus 375t plus 25 over 375, 3.75. Okay. So that's the solution for this straight that we've looked at this particular system of equation, constant right-hand side, constant coefficient and constant right-hand side. This is the solution here, at which point we're going to say essentially VA at 0 is equal to 0, and we're going to show that C1 is essentially minus 25 over 3.75. So the full equation here gives us what? VA for t greater than or equal to 0 is 25 over 3.75 times 1 minus 25t. Okay, so that's the solution here. When we essentially enforce V at 0 is 0, we get C1 is equal to minus that constant. So we can essentially factor that. So this gives you an idea. We're going to do some more examples based on this, but this gives you an idea of the kind of problem we can solve with step functions that operate like a switch. They function just about the same way. Okay, so let me just a little bit of review here. We started by introducing the step function, u of t. Okay, the function u of the step function u of t is a function that's 0 for t less than 0, just like I'm showing you here, and for t greater than 0, it's just 1. It operates like a switch. It switched from 0 to 1. That's what it is. It's a functional switch. So we can put step function in voltage and current sources. In this case here, I decided to put in a basic circuit with a voltage source. And once you see a u of t, you now need to think you have a switch at time t equals 0. So we solve the circuit for t less than 0. And obviously for t less than 0, the circuit, the capacitor, of course, behave like an open, but the circuit has no source. So everything is 0. This is what we call a zero-state circuit. Okay, circuit where the initial energy and the initial condition in the inductor or the capacitor is 0. So then we solve the circuit for t greater than 0 using a standard node analysis approach, finding nodes, put the reference node here. We write our source equation for the 10 volt here. V1 is equal to 10 volt. Then we write that 1 KCL equation at node VA. Okay. Then we do Ohm's law. For the 2 resistors we have, we put the Ohm's law into the KCL, collect terms. And after that, we write the capacitor. That's the capacitor equation right there. We write the capacitor equations. Okay. And then we bring the capacitor equation into the KCL and Ohm's law. That's what you have here. Collect terms, we normalize, and we get our standard differential equation. First order, constant coefficient. In this case, though, we have a constant right-hand side because, again, we have the step function essentially gives us a 10-volt value after t equals 0. Up to now, we've been looking at sources that after t equals 0 were 0 via the switches. This particular case is the reverse. After t equals 0, the source goes from 0 to 10 volt. So we get this, and then we can write the solution from that standard differential equation. And then now we enforce the initial condition here, which is VA at 0 is equal to 0, and we solve for C1. Okay. That gives us this final answer right there. Okay. So this is an example for a step response, a step function into a circuit. When you see the step function, you should think about it's operating like a switch at 0. Okay, where it's basically, instead of switching off, it's switching on. It's like turning a switch to flip the power into a circuit, a DC power. So that's what this is showing you. So we're going to pause and do another example to show you another flavor of a zero-state circuit. Let me pause for a second and pick up the problem. So I'm sharing with you a second problem for this session here. And I'm going to show to you that this doesn't involve a step function, okay? But it is actually a zero-state circuit, okay? And so obviously this is a problem that has a switch that is open. The switch is open, so the inductor is not connected to the circuit. So the switch is open, and then at t equals 0, the switch closes, connecting the inductor. So clearly the inductor has no current, so there is no energy stored in it for t less than 0. Am I making sense? So this is a particular problem here. It also involves a dependent source, so it's a little bit interesting. And I'm going to use mesh just to show you a different flavor compared to the nodal approach that we just used for the example with the capacitor. So again, let me go to the document camera. I'd like to do these particular problems on paper so that you see the process and you see my thought process as I proceed here. Okay, so let's do that. So I've actually just copied the problem on the document camera here. And I've rephrased the problem here saying calculate IL of t for all times, because the author, where I found this problem on one of the online texts, the author essentially assumed that the students will recognize that the initial condition for the inductor is 0. I want to address that, not assume that you actually can recognize this. What I want you to think when you see a problem like this, again, we talk about identifying the switch time is 0, and the switch action is important. In this particular case, the switch is open, and at t equals 0, it closes down. Okay, so for t less than 0, so what do we have here? We have the 1 amp. Our dependent source, which is 0.4 Vx. And we have this. And of course, the inductor is just hanging out by itself here, but there is no current on it. So clearly, IL clearly is 0 for t less than or equal to 0. Okay, so that clearly shows you that the initial energy on the inductor, of course, if the inductor was connected, we would say the inductor behaves like a wire, but the inductor is not connected to anything. So clearly, this is what? A zero-state circuit. That is a circuit with 0 initial condition. And we say 0 initial condition, we're essentially saying 0 energy initially stored in this particular, the inductor. The inductor is not connected to anything, so there is no power for it to charge up. Okay, so that's what we're talking about here when we're looking at this. So automatically right now, so the problem, if I show you, let me just go back here and show you. Just go back and show you the original statement. The author assumed you would recognize that because essentially saying determine the inductor current for t greater than 0. The author assumed that you will realize very quickly that the initial condition is 0. I just wanted to address that. I wanted to pretend that the problem asks you for the current on the inductor over all time, and then you could argue that for t less than 0, the current on the inductor is 0, thus the initial condition is 0. I wanted you to make that argument as opposed to just assuming you would be able to do that. So let's go back to the document camera here. All right. So then now we're talking about what? We're talking about for t less than 0. I'm sorry, for t greater than 0. Okay? We're talking about for t greater than 0. So what do we have here? We have our 1 amp. Our 10 ohm. Vx is here. Our dependent source, which is 0.4 Vx. Our 25. Oh, I had missed that resistor by the way here. Our 25 ohm. Our 5 ohm resistor here. And then obviously the inductor is connected. The 5 Henry inductor is connected. Okay, so that circuit we have for t greater than 0. All right, of course, we now know that the initial condition is 0 at t equals 0. Okay, so we're going to proceed essentially in a typical, we're going to do a mesh. We're going to do a typical mesh approach to show you the mesh flavor with a circuit with an inductor here. This is obviously a circuit that's going to give you not an homogeneous differential equation because you have that source in it. Okay, the source is not turned off. The source essentially is connected. So I'm going to go here. What am I going to go here? I'm going to go I1, I2. We're going to call this IL because that's what it is. Okay, so I put my mesh currents and I'm obviously using red to show you the mesh currents. Okay, we already have a voltage on the 10 ohms, so I don't need to do that. So let me put a voltage here on the 5 ohm, V1, a voltage here on the 25 ohm, V2, and for the inductor, V3. Okay, so I put voltage on my passive element, and I am essentially ready to solve this. So when we solve, so we're talking, this is a mesh, I'm doing a mesh analysis procedure. I set up mesh currents, put voltages. Of course, the 10 ohm already had the voltage because the dependent source depend on it. So I'm not going to add another voltage on it. So I put voltage essentially V1, V2, V3. Okay. Anytime we're doing mesh currents, we need to pay special attention to what? Current sources. So one source equation per current source. Okay, one source equation per current source. In this particular case, I1 is going in the same direction as the 1M, so I1 is 1. It's the easiest equation to write. Okay, this is also the case where the current source is only in one mesh. It's not shared, so we do not need to do KVL in super mesh. We don't do KVL in mesh I1 unless after mesh we needed to find the voltage across that resistor, that current source, but we don't do KVL in mesh I1. So I'm essentially, the next two equations are going to come KVL in mesh I2 and KVL in mesh IL. Okay, so this is my source equation here. So I go KVL in mesh I2. So what is it? Minus Vx plus 4Vx plus V2 minus V1 equals 0. Let's call this equation 1. Okay? Okay. KVL in mesh I2. Then I'm going to do KVL in mesh IL. So what do we get here? We get minus V2 plus V3 equals 0. Equation 2. Okay, so these are my two. I got my source equation first, and then my two KVL equation, one in each mesh, because these meshes do not have current sources, so I don't have to deal with source equations. I don't have to deal with with super mesh. And then we do Ohm's law. So Vx is equal 10 I1 minus I2. Okay. V1 is minus 5 I2. And V2 is 5 times I2 minus I3. So those are Ohm's law. Again, anytime we write Ohm's law based on the passive sign convention. Okay. So that's the next level here. Then I'm going to essentially have KVL plus Ohm's law. Okay. So equation one here become minus Vx. So I could, let's combine these two, minus Vx. So that gives us minus 0.6 Vx, obviously. So minus 0.6 that. So what do we have here? We have minus 6I1 plus 6I2, okay, plus V2 plus 5I2 minus 5I3 minus V1, so plus 5I2 equals 0. Okay, so collecting terms here. So minus 6I1, and then how many I2? 6, 11, so it's 16. Okay. 16I2 minus 5I3 equals 0. Okay. So of course, we know that I1 is 1, so I can use that. So that gives me what? Minus 6 plus 16I2 minus 5I3 equals 0. So that's my new equation 1. All right? Okay. So then equation 2, what do we have here? Minus V2, so minus 5I2 plus 5I3 plus V3 equals 0. Okay, that's equation 2. Okay, so that's equation 2. And then now for the inductor, what do I say? I say the voltage across the inductor, which is V3, is equal to the inductance, which is 5 DIL VT. So wherever I have V3 in my equation, I'm going to put 5 DIL D3 in my two equations here. So I only have one V3 here. So what do we got here? So equation 1 becomes the same, remain the same. It remains 16I2 minus 5I3 equals 6. I just moved the 6 on that's equation 1. And equation 2 becomes what? Minus 5I2 plus 5I3 plus 5 DIL dt. Of course, you can see the mistake that I'm making here. I'm carrying I3, but I3 is really IL, by the way. Okay. So again, my own mistake. I3 is really IL. Okay. I don't know why I introduced it I3 instead of IL. All right. So I3 is really IL. All right. So you can see here now I have two equations, two unknown. Two equations, two unknowns. Okay. So I solve for one and substitute. So I can solve for I2 from here. What do I solve? I solve for I2. I2 is what? 6 over 16 plus 5 over 16 IL. Okay. And then I use in here. Okay. And then when I do that, you can see the differential equation coming to play here. So if I do that, what do I have? Minus 5 times I2. So I get minus 3016 minus 2516 IL. Okay, that's the minus 5 times I2 plus 5 IL plus 5 DIL dt equals 0. And you can see my differential equation coming in here. All I have to do is collect terms and then normalize so that the highest order derivative is 0. Okay? All right. So, and when I do that here, what do I have? DIL dt plus, let me do some calculation here. So if I did my math correctly, collecting terms and normalizing, I get my differential equation to be that. Okay. All right. So that, what does that mean essentially? I mean, IL for t greater than or equal to 0 is equal to C1 e to the minus 0.6875t plus 0.375 divided by 0.375 divided by 0.6875. Okay. And of course, my initial condition is going to be IL at 0 equal to 0. Okay. So the final result is, let's look at this. 375 divided by 0.6875. 0.541 minus e to the minus 0.6875t. That's the end result for essentially our problem here. This is 545 times 1. So you can clearly see for t equals 0, the exponent goes to 1 and the initial conditions goes to 0. This is actually a fairly interesting problem because it also shows you a zero state circuit. Zero state because the initial energy, the initial condition, and the inductor in this case is 0. Then we proceed, this involves a switch, it didn't involve a step function, but we proceed essentially the same way, looking at for the circuit for t greater than 0. Now that we realize the initial condition was 0, we carried a mesh. We had a current source on the perimeter in one mesh, so that involved our source equation right there, I1 basically being 1. Then I end up carrying 2 KVL in the 2 meshes. Then Ohm's law, of course, I made a mistake calling IL I3, but that's that important. We could always reverse. That's what I did here. We put in the Ohm's law, KVL and Ohm's law, the 2 equations, KVL and Ohm's law, in collecting terms. Okay. And then we bring in the inductor. Passive sign convention applies for the inductor. V3 is 5dIL dt. I bring that into the 2 equations here. And then at this point, I should be seeing 2 equations to unknown. I solve for one, substitute in the other. So solve for I2 from the first one here. So I2 is expressed in terms of IL, and then I plug that in the second equations, and then here comes my differential equation. Then I normalize, then I apply my initial conditions to get the constant C1. So these are problems that requires a fair amount of practice because it brings in not just mesh and nodal, but it also brings in differential equations. But for my purpose, again, once you get the differential equation, I expect you can write the solution. No proof needed. I can basically write the solution based on the standard differential equation solution that we've discussed. I hope that helps.